Okay. Okay. So let me welcome you on the first birthday of the meetup called Technology Hour. Thank you all for coming. First of all, can I ask you how many of you are first timers? Okay, thanks. So for those of you who are here for the first time, don't leave these premises after the talk. We will move to relax room across the hall, where we will enjoy fruity discussions, and there will be food and drinks, and you can chill with Adam or together. So don't leave, and I thank you for coming. So Adam, it's yours.
Okay. Thank you. Hello, my name is Akka Warski. Thank you very much for coming, and thank you for the invitation. So I would like to talk today about the Reactive Manifesto and how to implement it using Akka. So how many of you heard about the Reactive Manifesto at all? Okay, so there's quite a lot. So it's very popular to be reactive, right? And it's some say it's only marketing, but there is some technology to it as well. And yeah, we'll see what kind of technology it is. Okay, so just to go through the Reactive Manifesto points quickly, just as a reminder, there are 4 main traits in the Reactive Manifesto that a system should have to be reactive, right? So the first one is, and it's like the most important one, is that the system should be responsive. Responsive meaning that it should respond in a timely manner to user requests, if at all possible. So if your whole system isn't down, right? So that builds user confidence that the system actually works, right? We need to provide some consistent quality of service. And the other 3 traits kind of help to implement the responsiveness. Okay, so the second one is that our system should be resilient. So here we have things like replication, so data replication, service replication as well, so like clustering. We have things like that errors should be contained as much as possible, so an error in a single component shouldn't spread to other components. That's also like isolation, right? And if a component cannot handle an error, it should be delegated. Then we have elasticity. So the system should stay responsive under varying load. So as the load increases, we should, well, hopefully dynamically increase the resources available to the system so that it can handle a higher load, right? And when the load decreases, we don't want to spend too much money. The resources should be deallocated. Finally, reactive. So that's like the message-driven trait is the most technical one. So reactive systems should be message-driven, and the main part here is that the main emphasis is on asynchronous communication. Okay, so we want to have components which communicate asynchronously, and when you design systems that way, it is much easier, or it is rather much harder, not to create a system that is loosely coupled, and we get location transparency, but we also have some additional problems that we need to solve, like load management, flow control, back pressure. When we have some components and they communicate with via messages, right? We don't want one component to flood another component with messages until it dies, right? So we need to have some way of signaling, I have too many messages, please stop sending me more requests, or something like that, right? And this should propagate throughout the system. So that's flow control, and back pressure is the signaling that we can't handle the load and that the message rate should somehow slow down. Okay, so that's like the Reactive Manifesto in a very quick summary, and we'll see how we can implement some of these traits using some of the Akka components. Just a quick note about me, so that you know more or less who am I. So I'm the co-founder and day-to-day a software engineer at Software Mill, which is a software house in Poland. We mainly do software in Scala and Java. I'm involved in a couple of open source projects. For example, Macquire, which is a dependency injection library for Scala, and there's ElasticMQ. Supler, if you haven't heard about it yet, it's our new project. It deals with a quite boring matter, which is web forms. but it uses Scala, so it's cool. So yeah, it will take over the form editing world soon, I'm sure. And yeah, I have a blog and a Twitter account, of course. So yeah, invited to visit. Okay, so now that we know who am I and what's Reactive Manifesto, what is Akka, right? If we go to the website and if we take a look at what's written on the website, we can read that it's a toolkit and runtime for building highly concurrent, distributed, resilient, message-driven applications on the JVM. Right? So that's about all we need to be reactive, right? We just use Akka and that's it. Okay? At least according to that description. So the core, at the Akka core, there's a lightweight actors implementation. Do you know more or less the actor model? Is everybody nodding? Yeah. Okay. So yeah, actors, like they contain some mutable state, and the only way they can communicate is via messages. And each actor processes message. It is guaranteed that the messages sent to each actor are processed on a single thread, so serially, not concurrently. So that way, the mutable state is protected. So Akka contains a lightweight actor implementation, and there's some error handling of the actors, but that's the core. That's the Akka core, but in fact there's much more. So there's a number of more or less experimental modules which provide additional functionality. So there's Akka remoting, which allows you to communicate with remote actors which are not on the same machine. There's Akka Cluster, which we will use. That's built on top of remoting, and here we have cluster management, node discovery, gossip implementation, and stuff like that. There's Akka Persistence, which helps you to implement event sourcing and actually persisting the state of the actors. There's Akka Streams, which is the most experimental of the modules. There's no stable version yet, but they are getting close, I think. So Akka Streams contains an implementation of the Reactive Streams, interface, or how do they call it? Anyway, yeah, and they provide streams with back pressure. And there's Akka HTTP, which is what used to be Spray. And in fact, I think I was talking about Spray last year here. So now it's not longer Spray. It's Akka HTTP, and it's a library for defining REST-enabled servers and HTTP servers in general. Okay, so that's for the intro. Let's start our example. So we will be writing a very simple application, a client-server application with a client and a server, of course. And the application will, the server will receive a stream of data from the client. The clients will send information about flight data. Each such data element, I can show you over here. So we have some statistics. We have a stream of flight information. Each flight information consists of the origin, destination, distance between the airports, the time it took to travel, and the expected, like the scheduled duration of the flight and the real duration of the flight. So the clients will stream CSV entries like this here, right? So we can see that that flight went from, that's Chicago, I guess. I don't know what's the APA, but somewhere, and it took for probably 810 miles. And somewhere here, there's also actual elapsed time and the delay. Somewhere here, yeah. That's like the delay is summed up somewhere as well. So the client will stream CSV entries like this to the server, and the server will try to calculate the flight with the largest delay per mile. Okay, so like what's the flight in which it was, which had the largest delay for each mile flown. And I have a model ready for that. So it's not very interesting. So we have a flight data class, and in the flight data class we have the from and the to, so that's the origin and destination airports. We have the distance between the two airports in miles, and we have the delay of the flight in minutes. right? We have a method to create a flight data class given a parsed CSV line, right? So that's an array of strings, so that's a line separated by string, right? We take that line and we try to get the appropriate fields and parse the numbers. If the parsing fails, then we return a none. Otherwise, we return a sum with the flight data inside. Okay? So that's all we need so far. Okay, so let's start by writing the server receiver. Okay. Yeah. So the receiver will be a class. It will take as a parameter an address. If there's like anything is unclear, just please ask. Okay, if you, for example, don't know some of the Scala syntax I'm using, let me know as well. Or if I'm just not talking clearly enough. So we will need an address. We will also need an actor system. So everything that we are going to do is based on Akka, and the entry point to all Akka, to anything in Akka is an actor system, which we have to create when we start our application. Okay. So here we have two parameters. We have the address on which the server will listen, and we have the actor system, which we will use to actually create the actors. Okay. We'll have a single method run. Okay, so the first thing we need to do is we need to bind to a socket. But we are not just going to bind to a socket. We are going to use the Reactive Streams API to actually receive the data in a reactive way. And what it means, I will explain in an example. So instead of binding to a socket, I will use the Akka Streams TCP support. So stream TCP, I'm binding to address, and for each connection, I'm going to do something, right? So here I have a stream of connections. So now for each connection, I will just print out some information that receiver, sender connected. Okay, so that we have a new client. Okay, so now inside the connection, I have a flow. Okay, a flow is a reactive stream which has an input and an output. Okay, here we have the output is what the client sends to us, and the input is what we reply to the client. Okay, the byte string, it is like a better array of byte. Okay, it has some additional operations which enable to concatenate to byte arrays, to add new bytes to an array, and so on, in a more memory-friendly way and in a more efficient way. Okay, so we're going to take that flow. So on the output, right? It has whatever the client has sent us. So we want to take that output and we want to transform it somehow. Okay. So the first thing we are going to do is we are going to transform the output from the client. So the output from the client, right? Using a parse line stage. Okay. This will unsurprisingly parse the lines in the output. So we receive a stream of bytes, right? And we want to chop them on the new lines to get nice strings. And that's just some buffer size. That should be more than enough. Okay, so now we have a stream, and on the output we have a stream of strings, right? Because we have transformed the bytes to strings. So now we want to filter that stream, and we want to only get lines which start with 20, and that is because if you look at here, there are some headers here, right? So we don't really care about these headers. We want to filter them out. So if we filter on lines which begin with 20, we should be good. Okay. And then we split each line, no caps lock. We split each line using a commas, right? So now we had a stream of strings. Now we have a stream of array byte, right? Because the split method returns an array byte. Now we will use map concat. Let me first write it. Okay, so if you know Scala map concat is a bit like flat map, so it takes
so
one.
maybe one question.
Yeah.
I'm just what is not clear to me is that how do you transform from byte array into a string? Is it somehow implicit?
From byte array to string. No, I'm going the other way, right? Because over here. So this is a stream which has an output of bytes, right? And I add a transformation stage here, which
So
takes the bytes and spits out strings, delimited by new line.
Yes,
Okay? And then I again split it, so I turn it into an array, array string, not array byte. Sorry. Of course, array string. And map concat, so it takes one element and applies a transformation which can result in any number of other elements which should be added to a stream, right? So applying flight data to an array can result in 0 or 1 elements, right? 0 if the numbers are, for example, in the incorrect format, right? Or if there are not enough fields, if the line is malformed, or 1 if everything is fine. So right, so that list over here will have 0 or 1 elements, right? So now we have a stream of flight datas, right? And yeah, okay, and that's we are not going to do any other transformations. So what we have defined here is again a flow, right? A flow on the output we have flight data, and on the input we have bytes. So we have to send back bytes to the client. And that is a part of a reactive stream. Now, a reactive stream can have a reactive stream has 3 parts. There is a source which has exactly 1 output. There is a flow which has 1 input and 1 output, and there's a sink which has 1 input, right? And when you combine all of these, you get like a closed pipe, and that's like the whole reactive stream. So what we have so far is the middle part. That's the flow. Okay. So now we need a source and a sink, right, to complete it on both sides. So we are going to attach a sink here. So it will be a very simple. It will be a very simple sink for now. Sink for each flight data. Okay. Scala DSL. And we are just going to print line got data. Flight data, just so that we can see that it actually works. And we are going to simulate some long calculations sleeping for 100 milliseconds. Okay? So now we have a sink, right? Because we had a flow and we attached a sink. So like if you look at as a whole on these 2 elements, right? There's only 1 input. So it's still a sink, right? So a flow plus a sink is a sink. So that's our sink. And we need to complement it with a source. So we are not really going to send anything to the client ever, because we are only accepting data from the client, and we will calculate the longest delay, but we are not ever sending anything. So we will take an empty source which never sends anything. Scala DSL. Okay, and we are going to complement the source with our sink. Okay, and that's our flow. Okay. Okay, so that's more or less our reactive stream definition. So now that we have the definition, why can't we just take usual socket and use lists or whatever data structure we use normally? So the key here is the back pressure, right? So here we have a fragment which kind of is slow because processing one piece of data every 100 milliseconds isn't really fast, especially that the data file, that one that we are going to use, it has like 500 megabytes. So it's quite a lot of flight information. Okay? So what is important here is that we are never going to overflow the memory. So once we reach that stage, right, that stage is going to process data slowly. And it is stopped as it is going to process data slowly. It's going to be like it's going to stop signaling demand for more data. And as soon as it stops signaling the demand for more data, this is going to propagate to the previous stages, over here and over here and over here, and it will reach the beginning, which is our socket, right? And the moment there's no more demand to read from the socket, the underlying I/O implementation will stop reading data from the socket, and the socket buffers will fill up, and this will propagate then to the client which is sending the data, and this will propagate even further so that the client will actually stop reading data and sending it over the network. Okay? Is it more or less clear? Not really. Okay, so how reactive streams work is that each component signals demand to the previous components. Okay? So once it has some free capacity, it says, give me 10 data elements or 100 data elements and or whatever its capacity is. Okay?
Can I have a question?
Yeah.
So I'm not that much familiar with Scala or Akka. Is it like that these transform filter map are like run in some specific processes? Like
yeah, but that's more like of an implementation detail. They are, and I will talk about it in a second. But like the general idea is the same. So the reactive streams. The Reactive Streams initiative, there's like a whole initiative around it, and there are a couple of implementations. Akka is only one of them. There's one for Java, there's one for JavaScript, so there's RxJava, RxJS. There's also some other one which I don't really remember right now, but there's a couple of implementations, and like the whole idea is the same. And the fact that there are some actors behind, it's only an implementation.
I don't have to care if it's like synchronous or
it is asynchronous.
Okay.
Okay, so how the reactive stream works is that each component signals demand to the previous components, right? So the sync will be the first to signal demand. It will say, give me, I don't know, 10 elements, right? And this demand will propagate all the way up here to the socket, and the socket will send 10 elements, right? And then the data will flow and will flow, but at some point, so the data will flow down and the demand will flow up, okay? But at some point, the sink will be all full because it didn't actually yet process all elements because it's sleeping here, right? So it will stop signaling demand, and so the demand will stop flowing up, and this will cause no more data to be sent down, okay? And the moment that the sink processes enough data to signal demand, it will signal the demand. The demand will again travel between the stages all the way to the socket, and the socket will start sending data again down. Okay? And what happens at the socket? So that's why we are not using a normal socket which would just read data as it comes. We use the reactive TCP extension so that data is not read anymore when there is no demand from the downstream stages, right? And this causes, when the TCP buffers fill up, that the information that no more data is read will be propagated to the client, and if the client is reactive, like it's not like there is no special protocol, it's just like plain bytes traveling on the network. But if the client is reactive, it will notice that it cannot send any more data to the socket, and it will also stop the client from producing new data. But we will see in a second. Okay, so that's like the general idea. Is it more or less clear? Yeah.
Question. Sure. How do you define the capacity of the sink? Is there some configuration?
Yeah, like these built-in components, they have like a predefined. So this usually depend on whatever demand is sent from the downstream route. But if you, we will define a custom sink, and then we will define the capacity. Yeah. You had a question?
I'd like to ask why the connection is flow and not the source, because I think it is the source of the data.
The what? Sorry.
Why the connection is flow and not the source?
The connection, because it has an output, which is what the client sends us, and it has an input, which is the data that we send back to the client. So it has an output and an input. But we don't really send anything to the client. That's why we use an empty source to just plug it into the thing. Okay, so what we have defined here is just a description of our reactive stream. When we run that code, nothing will happen. Okay, it is just a description. Now we have to actually materialize that description to actually have something happening. So what we have to do is we have to add a .run over here, and that .run uses an implicit flow materializer, which will use an actor flow materializer. So this means that to actually run the transformation stages, actors will be used. Okay. So for each transformation stage, an actor will be created whenever we run the run method. Okay? It is possible to store such a description of a flow in a variable, in a value, and reuse it multiple times. Okay?
One actor, or whole actor system will be?
Well, there will be multiple actors. Each transformation stage is one actor. Okay? So there will be one actor doing mapping, one actor doing filtering, one actor parsing the lines. Okay? Okay. So now we need one more thing, which is the actual application we will run. And we need to create the actor system. And we need to run the receiver with an address localhost 921. That's just a random port. Okay, so we have the server. Now I will also quickly create the client, and we will see if this actually works. Okay. So that's our client. And again, we have to create an actor system, as everything is actor based. And IDEA is doing something weird, whatever. So now we will connect to the server, stream TCP again, because we will have a reactive client which is aware of the reactive streams. So before we bound to an address, now we are going to establish an outgoing connection to the address that we used before, which is localhost 910. Yeah, like that. Okay, so we have the outgoing connection. Now we will have a method. So we will read the file, that file over here. So we are going to read the lines of that file and send it over the network. Okay? So we are going to use a Scala source. So that is a different source than the reactive source. Okay? So the Scala IO source simply reads data from file and gives us a lazy iterator of over that file. Source from file. And now I can make a mistake. Project. Data 2008, so we are using data from 2008. Okay, and we are going to call getLines. So that returns an iterator, and that iterator is lazy. So data from the file will be only read when we actually proceed with the iterator. Okay, so now we are going to create a reactive source. Okay, so the source, like we saw before, lines source. We are going to import the Scala DSL source, as you can see here, and we are going to pass the getLines iterator, and we are going to map each line so that we create a byte string for that line with the delimiter, right? Because we need to send strings. So that's our source, and our flow will be lines source via the server connection, which is a flow. Okay, so the server connection here is also a flow, but this time, right, it has an input, and that's what we send to the client, and it has an output, which are the responses from the server. Okay, and we need to attach a sync. So it's just going to be an onComplete sync complete. Okay, so the server is never replying, so we don't really care what the server sent. And implicit, again, we need to have the materializer, flow materializer, and flow run. Okay, so that's our application. I will just add one more thing. We will add some logging so that we can see how many bytes is actually read from the file. So that what should happen, right, is because the data processing is quite slow, only one item each 100 milliseconds, we should see some bytes read initially from the file, right, and then all the buffers should fill up, and until the sink in our server processes enough to generate new demand, that demand should flow all the way through all these stages here over the network to the sender, and then we should only get a new portion of lines. So we'll create an actor which measures bytes per second read from the file. Bytes per second actor of bytes per second actor. Okay. And we are going to length. We are going to send the length of, and it will just log how often, how much data was sent. Okay, so let's run the server first. That's the application. The server.
Can I ask you?
Yeah.
You created a materializer in the previous file, but you were using it nowhere.
Right. So it's an implicit value. And implicit is a Scala mechanism for passing parameters without actually having to write them. So if we look at the signature of run, you can see that there's a second parameter list, which is but you probably can't see that because it's small, but there's an implicit materializer, and it's going to be passed in automatically. So I could just write it like that. It's the same. It's just some Scala magic, let's say. Oh, you would be surprised. It is actually very useful. But yeah. Okay. I'm not sure it wrote complete here, but you can see that initially it read 800 kilo, right? And that now no more bytes are read because the receiver still churns the data, right? That's our server. And at some point we should probably, oh, here's the next portion being read from the file, right? So the whole file is 500 megabytes, but we only read small portions, only as fast as the server can actually process the data. Okay, and eventually the next portion of the data will be read. So what is nice here is that there's the protocol. There's like no special protocol over the network of actually signaling the back pressure. Only like standard TCP mechanisms are used of when the buffers fill up. That's noticed by the stream TCP extension, and normal demand is generated on the client and on the server, right? So no demand on the server propagates automatically to the client. Okay, so that's step one. Now let's do something more. So we wanted, yeah. Well, if the sender wasn't reactive, right? Like it depends, like how the sender was implemented. Like it could read data from the file indefinitely and just buffer up on the socket, and eventually it would go out of memory because like there's not enough. Like if we, for example, I guess this would have 64 megabytes of RAM allocated, and the file is 500 megabytes. So it would blow up eventually, right? If we just read it into the memory and buffered in the memory without sending it. But it depends on how the client is implemented, right? Like in a naive implementation, you would get an out-of-memory exception. Okay, so now let's actually process the data. So we will create an actor which will run on the server, which will calculate the largest delay per mile flown. Largest delay actor. Okay. So now this will be a reactive actor. Okay. And what it means, I will explain in a second. I can close that. Okay, so it's going to be an actor. Okay, and as an actor, I need to implement a receive with actor subscriber. So that's the reactive part. So when we create an actor with an actor subscriber trait mixed in, it means that it will be reactive aware. So it will be reactive of the demand generation and so on. So when we mix in the trait, all messages that arrive to our actor will be wrapped into on the next object. Right? So when we get sorry for the weird things that IDEA does, it's not my fault. So when we get next data, flight with delay per mile, we are going to calculate, so that's a helper class which takes a flight data, and if there is any delay in the flight, it calculates the largest delay per mile. Okay, that's very simple, right? We take the delay minutes divided by the distance flown in miles. Right, but if there's no delay, it returns a none. So if there is a delay, we are going to process delay data. Okay, we are also going to store the largest delay. Initially it will be none, and that's a type. Delay, that's a type, none. Process delay data. Okay. So largest delay, we take the maximum of the two. Okay. So the that class implements comparable, right? So we can just take the maximum from the list. Okay. So yeah, so here we will be storing the largest delay, and when our actor receives new flight data, we will update our internal state, right? And because it's an actor, it is guaranteed that only one message will be processed at a time, right? We'll also support a log largest delay message just to see on the screen what's happening. Print line largest delay so far. Largest day. Okay, but we still haven't done anything reactive here, right? We need to somehow signal demand, right? We have to define our capacity, and so on. So what we have to do is we have to implement a request strategy, and that's like comes from the actor subscriber trait, which comes from the reactive extension. So we will use a max in-flight request strategy. Very nice long name. And we will define that the maximum number of messages that can be processed concurrently, or at a time, let's say, not concurrently because it's an actor. So the maximum number of messages that can be processed at a time is 10. And we will have a counter specifying how many messages we are currently processing. Okay? So, and that is actually going to take care of signaling the demand appropriately for us. Okay, so what we are going to do here is before processing a message, we are going to increase our counter, and after, we are going to decrease it. So, as of now, it doesn't really have much sense because the actor processes one message at a time, right? So what we are doing is we are receiving the data, we are increasing the being processed counter, we are processing, which is just updating a variable, and decreasing it, right? So currently it will always be 0. Almost always 1 or 0, right? But it will change, of course, in the future. But like if we had, so processing could be in the general, of course, it could involve communication with an external system. It could involve writing to disk. It could involve communicating with other actors. So the counter here could easily then get to other values, right? And what this strategy does is that when we process a message and the counter is sufficiently low, it will automatically send demand to other components, like to the upstream components. Okay, so now we are going to use our largest delay actor. So instead of that sync, which was just logging stuff, we will send it to an actor sync. So first we have to create the actor. Okay, so we are going to create the actor. System actor of props largest delay actor. Yeah, and that's actor system. Okay, so we are going to have a sync. Instead of that, we are going to have a different sync, and our sync will be an actor subscriber, and it's accepting flight data, right? Largest delay actor. Okay, so now, like in our reactive flow, right? When we have created the flight data class, we are sending it to an actor, okay? And that actor subscriber will generate demand. So initially it will only generate a demand of 10, right? Because that's the maximum we can handle that we have defined, right? And as we consume messages, it's going to provide more demand, and that demand will never exceed 10 in total, not processed. Okay, so one more thing. We need to schedule logging of like our current maximum every second, so that we can see that something actually happens. System scheduler schedule 0 seconds, 1 second, largest delay actor. We are going to send each second, and I'm going to use the right variable. We also have to import the syntax, the 0.second syntax by import scala concurrent duration. Okay, so this gives us that syntax, right? And we are going to send each second a log largest delay message to the actor, which will print that to the screen. Okay, so let's try again. First we run the server, right? And there's an error. Missing parameter type for expanded function. Whoa.
You have to receive define it returns unit.
Yeah, thank you very much. I should have run the receiver first because it needs to bind to the socket. Okay, so there are no clients, right? We have no data, so we have no largest delay yet. We start a client, and the data will start flowing. And yeah, we saw that we have some initial data processed, and now the data is processed much faster because we don't have the 100 millisecond delay, right? So the data flows all the time. And we can see here that we have some, so we can stop this now, that we have some calculations, right? So initially there was a flight from, well, somewhere to Phoenix, which had 98 minutes delay per mile, and then there were some worse. Okay? So you can see that the data changes here, and that the data is processed in our actor. Okay, so far so good. However, we have implemented only one part of the Reactive Manifesto, which is being elastic, right? We react to changes we provide back pressure in our message-driven system. But what about being resilient? So when our server crashes, we lose all data, right? So how can we fix that? Well, that's quite easy. We can use Akka Persistence to actually persist the state of the actor, okay? So instead of actor, we will extend persistent actor and do a couple of more changes, but they will be quite small. So we extend persistence actor. We need now to override, we need to provide a persistence ID, which is kind of a key that will be used in the database to store that actor's state. So by default, Akka Persistence uses local level DB storage, but there are plugins which allow you to use it with Cassandra, Mongo, and other storages as well. So especially when, for example, when using Cassandra, it is quite easy to have replicated storage for an actor, right? Because Cassandra is quite easy to set up with the replication. Okay, so what we are going to do is instead of receive, we now have to implement receive command. So receive command is what is being called when messages arrive in like normal state of operations. So that's our previous receive. And when we actually have the data, we are going to increment our counter. But now we are going to persist the event. Persist async. Okay. And only after our event is persisted, we are going to process it. Okay, so persist async, what it does, it persists the event. So here our event is the flight with delay per mile. Persists the event on disk. And when the event is persisted, it calls the given callback. Right? So now our in-flight counter can have a value from 0 to 10. Right? Because we first increment it, we then call persist, and only when the persist completes, right? The persist is asynchronous, so the callback is so there may be like other messages being serviced before the persisting proceeds, before the persisting completes. So we may start persisting other items before the first one completes, right? So we don't decrement the counter until it's actually persisted. Right? So if for some reason the disk is currently slow and it doesn't accept any more writes, our counter is going to reach 10, and there's no more data will be processed, right? No more demand will be signaled, and data will stop flowing in the entire stream, like gradually. Okay, back to it will propagate back to the client. Once the data is again being persisted to disk, all the stream will resume processing the data.
Now this can be done in parallel in another thread, or is it?
Is that done in parallel? Mm-hmm. So yeah, so the actual persisting, because there is a persist sync method, but here we are persisting asynchronously. Async. Sorry. So we are persisting asynchronously. So yes, so that is like there is a separate actor which actually writes to disk. So this actually sends the data to be written as bytes. So that's serialized to bytes. So this sends data as bytes to the actor which writes to disk. And only when that actor writing to disk completes, that callback is done. But before that happens, right, we may service other flight datas.
Right. So the in-flight variable or any other data structure should be thread safe, right?
Well, no, it doesn't have to, because that callback is still executed like inside the actor. So the actor always services at most one message at a time, right? Mm-hmm. So actually running the callback is also done like inside in response to some internal Akka messages. Uh-huh. So that doesn't have to be thread safe. No. So that's like all in one actor. Right? Here we have a wrapper which says, here's the user code to serve the flight data, right? There's also some internally in the persistent actor, there's some code saying, when I receive a message saying, hey, I persisted your data, yeah, run the callback. But it's like in this actor. Okay? So we also have to implement a receive recover method. Recover. And this is going to be run when an actor is recovered from persistent storage. So when an actor is recovered, all the events that have been saved will be replayed and passed to the receive recover method. So when we receive the flight with delay per mile, so that is done on the actor's startup. We just call the process delay data. So on actor's startup, if there is any data persisted for that actor, each message will be passed to that method. Okay? We don't need any reactive stuff here because that's just done once at startup, and like Akka takes care that it is done in an appropriate way. Okay, and that's all changes. It's not a lot of changes, but now our data is persistent. So let's run our server again, and yeah, there's no data so far because we didn't have persistence before. We run our client. Okay, you can see that some data is being processed on the server, right? So now we of course kill the server and the client, the client and the server, and we run the server again, and hopefully the data will be recovered. Yeah, you can see that even though there's no client, the data is here, right? So the data was written to disk, and yeah, so that's persisted. Okay, so if we use that with the clustered storage, we are pretty safe. Like if the node is restarted, then we will recover our data. You can see that actually the journal that's used is over here. So that's where the level DB database is being stored. Okay.
So the data which are sent from client, but were traveling from
over the network, yeah.
Over the network, or were in the flow somehow processing, could be lost. But the data which are received by the actor was persistent.
The data from the there can be some data can be lost, sure, because we didn't really implement any mechanism to acknowledge that we have received messages from the client. Yeah, sure. Yeah. But it's like what we have managed to process, that will be saved. Yeah. Okay, so one final step, because we are now safe from restarts of the server, but what if the server dies completely, right? We need to have some kind of clustering on top so that we can have a couple of servers which actually will take over the job. If one server dies, the others will take over the job. Okay, so again here, Akka comes to the rescue, of course, and we will create a cluster on top of the mechanism we have so far. So in our cluster, so now we will be again implementing the resilient trait, right? We have resilient data, but we don't have resilient services yet. So what we will do is we will start a cluster of 3 nodes, okay? And we will define a cluster singleton. So we want to run our receiver server on exactly one node of the cluster, okay? And on one node, we will bind to the socket, we will listen for client connections, okay? So like the receiver server will have a separate networking layer from the cluster, which will have its own network, its own ports and its own networking. Okay, so what we have to do is we have to define a receiver cluster node class with a cluster port. So that port will be used for cluster communication, and that's different from the server port where we receive data from the client, right? So that's like internal cluster communication. Okay, and we define a run, and we need a config. So that's one part, the config factory. So now, so how Akka clustering works is to actually create a clustered actor system. You need to provide an alternative configuration, and the main part is that you have to override the Akka actor provider setting, and you need to provide the port over here and the host name and the seed nodes. Right? So given these settings, when you create an actor system, it will be automatically clustered. So it will try to form a cluster with the seed nodes. So what we have to do is we have to override the port in that configuration. So that's a bit clumsy, but I did complain about it. But they didn't listen to me for some reason. Akka remote net the TCP port. Right. With fallback config. So what we are doing here is we are taking that configuration file, right, cluster receiver template, as you can see here, and we are overriding that one property with the cluster port. Okay, now we are creating an actor system with that configuration. Okay. Now we want to create a cluster singleton, so we need to have some support for that, right? There needs to be some component which actually takes care of running our code on exactly one cluster node. So there's a cluster singleton manager for that, coming from Akka, of course. and it's an actor, so we can create it like that. Singleton props will be props. I will explain receiver node actor. We'll implement it in a second. So that's the actor that's going to be run on exactly one node. Singleton name is receiver. So that's just some configuration which needs to be entered for. Not really important here, but it's poison. Poison pill. Role is some receiver, and name is receiver manager. Okay. Okay. So what we have to implement now is one more class, one more actor. Sorry, I'm not sure why it blinks so. Class receiver node actor cluster port int extends actor. Okay, we need to import poison pill. Yeah, and actor. Okay, so the cluster singleton manager, it will run an actor on exactly one node of the cluster, right? So our receiver here, that class, it wasn't really an actor, it was just some code, right? So we need to wrap it in an actor so that the cluster singleton has an actor to run. Because it doesn't support arbitrary code, it needs an actor to run on the one node. So our actor, it won't really do anything. Override def receive is empty behavior. Yeah, it's not doing anything, but before starting the actor, it will start our server. New receiver with the address localhost cluster port +10, so there's no conflict. Context system.run. Okay, so we have an actor, and when that actor starts, it will start our receiver server, right? So that way, when the cluster singleton manager starts that actor on exactly one node, our server will be there. Okay, so that's almost it. Now we need clustered receiver node 1 extends up, new clustered receiver cluster node 1971.run. Okay, and we need 3 of those. That's 2 and that's 3. Okay, so we have 3 nodes. And let's delete the data so that we start fresh. Read the old journal. Okay, so now hopefully when we run that, we will see a 3-node cluster being formed. Or not. And that's closed, and that's not necessary. Okay. So that's node 1, that's node 2, and that is node 3. So now forming the cluster takes a while, like a couple of seconds. But eventually on one of the nodes we should see some, oh yeah, here we go. So these are our familiar log messages, right? So now let's start a client, of course, to actually send some data. Sender, right, that's our client. So let's start our client. Okay. It doesn't send any data because that's the wrong port. The first node is on 1981, right? So we need to provide the correct port. Now it's sending some data because it's actually connected to a socket. And we can see that there's some data here, right? Okay, so far so good. So now let's try, of course, killing one of the nodes. And as it is a cluster, the cluster singleton manager should notice that one node is dead, and it should run our singleton on another cluster node. Okay, so we killed the first one. And eventually we should see, like in 10 seconds, which is the timeout of actually checking that the node is dead for sure, we should see our receiver started on another node. And because it's all on one machine, the storage is shared, so it should even have the data, right? So we kind of emulate a cluster database. You can see that on node 2 the receiver was started as well with the data we had, right? So now we have a fully resilient implementation. Okay, so that's for the coding. Just a few final remarks.
I have a question.
Yeah.
The port the sender was configured is the port of the
Receiver.
Of
Yeah, so for cluster communications, we have been using 70s, right? 71
Yeah.
and 72. But to actually bind the receiver, we were using plus 10, right? So the node 1 was, if the receiver was started on node 1, it bound to 1981.
Yeah, it's still the same port even though the node changes.
On node 2, right, it would be 1982. Because we are adding 10 to the cluster port, right? So the port for cluster communication for node 2 is 1972, right?
Yeah.
And if the receiver starts on node 2, we are adding 10 to the cluster port, so it's 1982.
So did the sender resume communication?
Oh, no. So we would have to restart the sender with a different port number.
Yeah.
Okay. So that's one of the things that I wanted to say. What's like, there is a to-do list. Yeah. There is a to-do list. So as you noticed, we would have to it would be good to discover where the receiver actually runs, right, on which node. And there is an extension for that in Akka as well. It's called cluster client. So we can connect to the cluster and we can ask, hey, where is the receiver actor actually running, right? So, and then we can get the correct port number to stream the data. Another thing that would be good to do is to actually reconnect the sender when there are some errors, run the connection is broke or something like that. And finally, in the persistence, like we always, when we restore from persistent storage, we always restore from all events that were ever recorded, right? So if like we have gigabytes of those, that could take some time, probably seconds, but still. So there is a mechanism called snapshots, which allow us to snapshot the state of an actor in time, and only and then you recover from a snapshot and all events after that snapshot. Okay, so there is a mechanism for that as well. Okay, so just to recap on the traits, right? We have implemented a resilience system using clustering and persistence. Using Akka clustering and persistence. It is obviously message-driven because we have used actors for everything. Even if the actors were not visible, like in the streams, there are actors in the background. And the system is elastic because we are using the reactive streams, which accommodates for varying loads on the various stages of the transformation. Okay, and. So there's a couple of links. So the presentation is here. We'll also send it to Jakub. There's also another small project called Reactive MQ, which is like a showcase project for the reactive Akka I have shown you here. It's a message queue implementation with all the additional traits I told you about here. So it has all those, well, it has those two implemented. So it has the discovery of where the server actually runs, and it has the it has the error handling. It's like a message queue built on top of the reactive streams and persistence. And yeah, that's the page of the reactive streams initiative. So there's like a TCK which implementations can implement and get I'm not certified, or I'm not sure what's the official word, but let's say certified for being reactive. And of course, there's Akka. And yeah, I guess that's it. If you have any more questions, I'll be happy to answer. Thank you.
Are there any questions? Okay, so I would like to ask Adam to select one winner of the t-shirt.
Okay. Okay. Tomasz, say Kora.
Say Kora.
Say Kora. Yeah, that's correct? Okay. Okay, and another t-shirt was for good questions, right?
Yes.
So I guess you deserve the good question t-shirt. Yeah. Okay. Putting it back.
Okay, thanks.
Okay, so
Okay,
yeah.
Let's move to drugs.